Welcome semiconductor students. In this short video I'll be discussing the advantages of using diodes and capacitors together to form what's called a clamper circuit. The word clamp indicates a fixing, and in this case what this circuit does is it grabs the lower end or the upper end of a sinusoidal waveform, in this case what's being generated by our V source here, and attaches it to a certain DC level. So it clamps the waveform to a certain DC level, hence the term clamper. So the way this works, and this is a quick review of the theory, on our positive going end of or side of the sinusoidal signal, we'll have positive current flow coming out of our source and charging up our capacitor here with an opposite charge. But because we can't continue to flow current very quickly through this big resistor, we've got a big time constant, and we certainly can't flow backwards through the diode, we don't really get a whole lot of charge on this capacitor during the forward cycle, basically from 0 to 180 degrees for our 360 degree sinusoidal cycle. But when we go the other way and the positive sign is down here and we're flowing conventional current in the other direction, we don't have to go up through this big 100K resistor. We can go through the diode in the forward direction and charge this capacitor up real quick. And in that case, we'll end up very quickly achieving the full amplitude of our sinusoidal source accumulating on this capacitor, and then as the voltage down below the diode drops, of course we've now got a big positive voltage on this side, and as we drop below our peak amplitude, which we should have achieved up here minus whatever our offset and our forward bias voltage is, we won't be able to keep current flowing. We won't be able to have a driver over our forward bias voltage of our diode. We stop flowing current and we stay with the charge we have, which will give that capacitor an effective voltage equal to whatever the peak of our source was minus the forward bias voltage of our diode and minus or plus whatever this DC offset is that we put in. We could of course flip that battery around the other way. So on cycle number 2, when our polarity switches and we start applying positive voltage back, sort of with conventional current flowing back in this clockwise direction, now we have basically 2 voltage sources in series. We've got our charged up capacitor, which will be positive going towards V load, and now we have a V source that is adding to it. And the capacitor never discharges. So because it doesn't discharge, it establishes effectively a DC offset. We could have done the same thing by just putting a second source. We could have put an invariant DC source, a battery, up here instead of the capacitor. But the capacitor has the advantage that because it's charging based on the amplitude of our source, we can apply this DC offset as a ratio of the amplitude of our source. And that's where the term clamper comes. Depending on the magnitude that we select of our voltage source that we select here and the forward bias voltage of our diode, we can select a certain fraction of the total amplitude of our voltage source with which to offset the total signal, up or down. So up or down based on the magnitude down here. The capacitor here will always lift it up. Of course we can turn our diode around and it'll go the other way. So basically that's the idea of clamping. By charging, because this capacitor will charge to a particular fraction of our amplitude of our source, it's excuse me, it is clamped, so to speak, to the source. So let's go ahead and run this circuit. Let's see what source voltage we're looking at here. Check it out. So we're going to apply a sinusoidal voltage signal. We're going to apply only 2 volts, and we're going to use a 1 kilohertz frequency. So that is That voltage is not too far above the forward bias voltage of our diode. This should be somewhere between 0.3 and 0.7, depending on how much current ends up flowing. This is a small signal diode, and we are applying what looks to be 1 volt down here. So, and it's going in the same direction. So basically, we won't get current flowing in this clockwise loop until we have gone basically 1 volt plus the forward bias voltage in basically the negative going direction. So that's going to affect the DC offset that we end up getting. That will affect how much voltage we can accumulate, how much charge we can accumulate, excuse me, and the accumulated charge will, of course, based on the capacitance that we choose, give us a set voltage which won't discharge. Okay, enough theory. Let's go ahead and run this with 1 kilohertz frequency. We're going to use 4 milliseconds, which will give us a couple of wave periods so we can get an idea of what's going on. Remember, the first forward going period, nothing's really happening. We charge the capacitor on the second, and then we should see our clamping effect on the next forward going cycle. So we'll go ahead and run this. See what we have here in terms of, let's go ahead and blow this up. Take a look at what signals we have. And the Y scale is not centered. So let's use a legend, see what we got. So V source is in green, so that will be centered on 0. So let's just scan across, take a look at it. So we've got the 2 volts. You can see this in the Y cursor display in the little A signal, tracking it, and then it's centered more or less on 0. We go about halfway down the waveform, and then we have a -2 at the other side. So we have definitely clamped our V load, and let's go ahead. This is actually, we have a derived signal here in the bright red that I'm following with my cursor that's kind of tracing the bottom of the screen. That's the actual voltage drop across the capacitor. So you can see it charges, it doesn't charge on that forward going cycle, and then it charges up to a given level, and then it stays pretty level and just has a very small perturbation as we go. So this voltage over the capacitor, that's our offset. And so that's what's actually giving us our clamping or our elevation of our signal here on V load. And now I'm tracing V load, so that's what our output would see. So at first it's seeing just the forward bias voltage difference from the source going up because we're not really doing much to that capacitor. Now we reduce the source signal. Now we go down past 0, and now we can flow current the other way through the diode. We're charging the capacitor. Now we're swinging back up. We go past 0, and now that capacitor voltage is adding to our source voltage, and so we really don't go negative again. If you look at the printout, we don't really drop below 280 millivolts. So rather than going from -2 to +2, we're going to something around 4, and then we bottom out at 382 now. So basically what we've done is we've taken our source voltage, we've elevated it such that the negative most point has been raised by the amplitude of the source plus or minus the forward bias voltage of our diode and the source that we're adding here. So we've got this 1 volt source that is going to raise this point up another volt minus what we would have to apply with the forward bias voltage. So that's why our bottom point is not at 0, it's at 382. So we're seeing the 1 volt minus the forward bias voltage of the diode. So we can adjust how much offset we want, how much charge we want to give us a voltage on this capacitor to basically be our offset by changing this voltage source, or by possibly getting a different diode with a different forward bias voltage. We can clamp negative. So we could basically charge this capacitor in the other direction if we wanted, and all we would have to do that would be to turn the diode around. So all of this is working because we are basically using the one-way flow of the diode to allow the capacitor to charge only on one side of the cycle and then block it so it doesn't discharge on the other side. And just as a hint, this circuit should look a little bit familiar for those of you who have done smoothing of a rectified signal. So as you all know, you would put a capacitor in parallel with your load coming out of maybe a diode bridge rectifier. As you can see, by putting the capacitor in series with our AC source, we create a clamper. So it's important, if you're using a smoothing capacitor, make sure that you have it positioned with your load, with respect to your load, such that you don't inadvertently create a clamper. Obviously, you would have to have it configured relative to one of the diodes from your bridge, but that is something just to be careful of. As long as we are only allowing current to flow one way, and if we put a capacitor in our circuit, there is always the possibility that we might change our voltage in a way we didn't expect. So clampers and smoothing capacitor circuits look a little bit similar. So let's move on and take a look at a couple of outputs from real circuits. So we're going to start with this exact same circuit output built on my protoboard. So I went ahead and took my TINA circuit and I replicated it on my protoboard. I used the same frequency input. I used 1 kilohertz plus or minus 2 volts, and put it directly into a clamper circuit, same resistor values and the same signal diode. And you can see that I got very similar results. A little bit of distortion of waveforms, but otherwise close to ideal. So we have our input signal in blue coming in on channel A, and then you can see the elevation of the circuit, the clamping that we have on our, on our channel B. That's the voltage drop over the load. And I got to make a correction. It is not exactly the same. I did not include the 1 volt battery in series with the diode, which is why I actually do go negative here. So in the TINA circuit, that value would be raised up here to about 382 millivolts. So it's the same as TINA minus the battery. So if we didn't have a small signal diode, maybe we only had an LED, something with a much larger forward bias voltage. This is the kind of result we might get. This is the same exact circuit, but with the signal diode taken out and a red LED added. So it doesn't almost look like we're getting any clamping. You can't really even see the DC offset, because in this case you aren't able to charge the capacitor until that negative going voltage signal exceeds the forward bias voltage of, in this case, an LED. Well, I'm only applying 2 volts amplitude. That's all my Picoscope AWG will give me. An LED has a forward bias voltage of something around 1.2 or more. So I'm only going to charge the capacitor such that it will give me an additional voltage equal to the amplitude of my source minus that forward bias voltage. So it can't get enough charge on it to give me a very big DC offset. It isn't clamping at a very high level in this case. And we actually had to go and do a measurement max min, and I'm circling that with my cursor now under channel B. You can have the Picoscope print this out on a PDF, which is what we're looking at. So if we look at the minimum over the whole tray, so the Picotech software looks for the minimum point and does an average of all of these waveforms that we're displaying here. It has a value of negative 1.63, and the maximum is 2.11. So it is clamped, it is displaced upward. There is a bit of a DC offset, but not nearly as much as when we were only having to subtract that much smaller forward bias voltage, which was the case for the signal diode. And I guess if we want to, we can just, we're winging it now. I'm going to go ahead and remove that battery, and I'm going to rerun my circuit and see how our values change, and then run back to my printout and compare. So I'm now tracing the output, the V load, which would be my channel B from my Picoscope, and on this circuit where I don't have the DC offset, and so now I am going negative on my negative cycle. So I'm at a 3.35, 3.7 positive going, and about negative 600. So a little more than 600 millivolts minimum, and about 3.3 maximum. So let's go back and compare it to what the comparable circuit was. A little bit more than 3, so here's our 3 mark. We look at the scale for the channel B in the red. So we can see that our peak is a little over 3, which agrees fairly well, and our minimum is somewhere between 1 and negative 1, and it looks like it's about a bit more than halfway there. So max-min is correlating fairly well with what we predicted with our TINA software once we remove that 1 volt battery source in series with the diode. Only differences with our real circuit, other than possibly some differences in actual max-min, is we are getting a little bit of distortion at the bottom of our minimum. Excuse me. Don't have a ready explanation for that, but we are definitely, if we compare that to what we would get, what we're seeing on our ideal model, there is some flattening there at the bottom. What could be causing that? There could be some RC charging. We could be looking at a little bit of a charging effect, a tail off, other non-idealities in our components. We have long cable, so we could have some unintentional circuit additions that we're not aware of. But that's just something to note, that we are getting a bit of what would be called clipping, possibly, going in that other direction. And that may indeed be one of the things that's going on. But definitely a truncation of the sine wave going in that direction. Otherwise, definitely seeing very equivalent to our ideal model in terms of the extent of clamping or DC offset that we predicted using our capacitor and our resistor. So we'll go back to TINA and just give a couple of hints. If you are constructing and designing your own clamper circuit, just some rules of thumb: you need to take a look at this RC portion of your circuit and the frequency that you're applying, and remember, what you need is to make sure that the time constant here is big enough that it's not going to charge kind of in the wrong direction too much based on the direction you have your diode. So in our case, we're clamping to a positive voltage. I don't want this left-hand side of my capacitor to charge up very much on the forward-going part of my cycle, because I'm going to want all the charge over on the other side where it's going to add to my V load. So I want a time constant that's big compared to the period associated with my applied waveform. And remember, your time constant is going to give you something around 60% of the total value. So go for something closer to steady state. Calculate your tau, which is just R times C. It's going to be in seconds, and then maybe multiply by 2, 3, 4, 5 if you want steady state, and that'll make sure that you get a nice smooth line, and your capacitor voltage is staying at a steady level where it will add or subtract as you want. So that's it for a clamper review. Definitely encourage you to grab your software and explore and compare to some circuit builds that you do with your protoboard and whatever signal generator and scope that you have, and look at ways to have a self-adjusting DC offset to your signal.